Okay, we'll start looking at examples of how to use these trigonometric ratios that we found before, the sine, cosine, and tangent. And here's an example. So we've got a triangle here. Looks very similar to the one we saw before. It's got a 30-degree angle. And the question's asking us, what is the length of side x? So side x is down here. This is what we would call the adjacent side to that 30 degrees. So I'll write an ADJ there to keep note. This side over here is going to be the opposite, so I'll write that. And then, of course, that 5, because it's the longest side of that right triangle, that's going to be our hypotenuse. So I'll write HYP. I guess before we even do that, we should look at this and say, can we solve this using Pythagorean theorem? Well, we know one side, and we want to know another, but we don't have the kind of third side, the other leg of this triangle. So we would need another number in order to find this missing side using Pythagorean theorem. So that means it's a good instance where we can use one of our trig ratios. So what we're going to do is we're going to look at what we know and what we want to know. We know the hypotenuse, and we want to know the adjacent. So we have, we have the h, and we want to know the a. So we have a and h that we're concerned with. We don't know anything about opposite. We don't want to know anything about opposite. A and h is where it's at. So that means what we're going to do is we're going to look at our trig ratios up here, and we're going to say which one involves a and h. Oh, it's this one here. It's cosine. So we're going to set up the skeleton equation for cosine, and I'm going to do that down below. So that skeleton equation, like we said earlier, is cosine is the ratio of the adjacent to the hypotenuse. So just write it out. It may seem redundant. You'll write this out initially just with nothing plugged in, but it's good to do. It's nice practice to get used to writing these things and kind of ingraining what cosine is. It's adjacent over hypotenuse. And next we'll fill everything in. So we'll fill in our angle, the theta, the unknown angle here. It's 30 degrees. So we'll say cos 30 degrees. Equals, well, the adjacent we don't know. Let's use the unknown x for it. And the hypotenuse we do know, it's 5. Okay, so now that we've got it filled in, this becomes an algebra question. This becomes a question where all we have to do is solve for x. And if we look at x as it stands, right now, we're taking x and we're dividing it by 5, so to get rid of that, we'll multiply both sides by 5. And what that'll look like is we'll have our x on the right, and we'll have 5 multiplied by cos 30 degrees. I like leaving it as cos 30 for now. Some people are tempted right away when they see cos 30, they grab their calculator, they say, I want to know what that is as a number. Well, we can figure that out, and we will. But it's nice to work with it just like as is, just because if you treat it as a number, right, and I'll type it in, I'll figure this out, cos of 30 degrees is 0.86602540378. The minute I cut that off, I'm losing a little bit of accuracy. So I like to keep my cos 30 in here as long as I can. And then I punch it all into the calculator at the end. So I take my number and I times 5 by cos 30. And when we do that, we get, and again, the calculator holds all those digits of cos 30, so we don't have to write them down. And when we do that, we get 4.33, and it's 0.127, da 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 da. But for now, we'll just leave it at 2 decimal places. So that means x is 4.33. So let's go back up to our sketch and have a look at that. So here's our triangle. This side here is 4.33. So what I recommend you do is kind of just take a step and say, all right, does that make sense? It's a leg of a right triangle, right? This is a right triangle we're dealing with, and the adjacent side that we just mentioned is 4.33. So it should be less than the hypotenuse, right? Hypotenuse is always the longest side. So if we get an answer of 4.33, that's probably pretty good evidence we got a pretty good answer, because it's at least falling in line with this idea that it needs to be less than, the hypotenuse, the 5. If you got an answer of 5.33 or something greater, you would look back and say, oh, maybe I made a little error somewhere in my calculations down below. So you'd go back and double check your work. Okay, so that's how we arrive at the answer to this. I want to take another minute and just look at this through the lens of similar triangles, because all we kind of did is we just pushed buttons on our calculator, and I feel like the way of working through this is very nice. It works, it uses a lot of algebra, but I just want to reinforce a visual kind of depiction of what this is. So imagine we have, I'll just sketch out 2 triangles. I'm going to sketch out one here and a larger one over here. And again, this idea of similar triangles is going to come into play. So that's why I had that included before. Now this is our larger triangle. So it's got the 5 up there. And I'm going to draw a smaller triangle here, and that's just going to hang around for us for a second. Oh, and it's also very important to note that they both have 30 degrees, of course, inside that small interior angle there. Okay. So when you press cos 30, right, cos 30 degrees, and you get an answer of 0.866, and it keeps going for a while, a bunch of random digits. That's a number, it's a decimal number, and I can turn it into a fraction, and that fraction I'm going to turn it into is that over 1, right? Any number I can turn into that over 1. Now the next thing I'm going to do is I'm going to say, okay, cosine of 30, remember cosine, the definition of what cosine is it's taking the adjacent over the hypotenuse. And in this case, the adjacent, again, is this lower one, and the hypotenuse is up here. So if it's adjacent over hypotenuse, then what I'm looking at is 0.866 over 1. So we're taking adjacent 0.866 over 1. The hypotenuse is 1. Adjacent over hypotenuse. Adjacent over hypotenuse. Okay, now, in a way, we're going to ditch the cos 30, right? Just kind of ignore that that's there. Now what we're going to do is we're going to tie in that idea of similar triangles. And that would mean we're going to consider this side here. Well, this is the side we want to know. This is the x. And when we think of this through the lens of similar triangles, what we can do is we can set it up by saying it's the ratio. Similar triangles tells us that the ratio of 2 sides are equal. So we can take that 0.866 and say, hey, that's equal to x over 5. And the reason we can say that is because we're looking at the lower side over the hypotenuse, and we're doing the same on the small triangle. We're taking the lower side and dividing it by the hypotenuse, because we're just enlarging the triangle, so we can take the ratios of corresponding sides and say that they're equal. Well, now at this point here, we've got ourselves, well, and in fact, we can get rid of the 1, can't we? We're just dividing by 1. What's the point? So you can think of it as, well, you can think of it as exactly where we were right up here. Cos 30 is 0.866 equals x over 5. Well, hey, that's exactly where we ended up. But the way that we did it is we did it through a lens of similar triangles instead. So I kind of like this as a way of looking at trig ratios. So it's just an alternative way of looking at this. Rather than, I find we get bogged down in the strict algebra and we start to forget like where these things came from. And this is kind of where this cosine, how this algebra works, is it connects this idea of similar triangles. So when you press cos 30 on your calculator, I just want to stress this again, when you press cos 30 on your calculator, in a way, it builds a little triangle inside the calculator with a 30-degree angle here. And if you're pressing the cos of 30, as opposed to the sine or the tan of 30, if you press the cos of 30, what it does is it takes this side, the adjacent side, and divides it by this side, the hypotenuse. And it doesn't matter how big the triangle is that your calculator makes. It could make a triangle that's as large as this one or one that's larger than your screen. As long as there's an angle of 30 degrees in there, when they take the adjacent and divide it by the hypotenuse, they're always going to get the same number. In this case, that number is 0.866. So that's kind of what's going on in your calculator when you're doing these questions. Okay, that was one example. Let's move on to another and try to solidify some more things. Okay, this next example, we're solving for another side. This time it's side G. Mix it up, use a different letter than X sometimes. And we're standing at this 40 degrees here, so we're going to label the sides based on that. So that means this 8.5 that's across from it, that is our OPP, our opposite. G, therefore, would be our adjacent. And then this longest side, of course, that's across from the 90-degree angle is the hypotenuse, as always. Doesn't matter where you're standing. That's the longest side. Okay, now we're going to say, what do we know and what do we have? Well, what do we know and what are we looking for? We know we have the opposite, and we're looking for the adjacent. So O and A, those are the two that we're looking for. That means we're going to deal with tan. So we're going to write out the skeleton equation for the tangent. And so we're going to say tan of some angle is opposite over adjacent. Start just by writing it out with nothing filled in. Next step, let's fill it in. The tan of the angle, which is 40 degrees, is going to be equal to the opposite over the adjacent. Well, the opposite is 8.5. The adjacent, well, hey, that's G. That's our unknown, so I'll use a G there. Now, to get G by itself, now think of it from an algebra perspective. To get G by itself, as it stands, it's kind of tricky because G is on the denominator. So let's move it up to the numerator. We can do that by multiplying both sides by G. That is to say, we can write it out as G tan 40 equals 8.5. Right, if we multiply both sides by G, then this G cancels out on the denominator here, and it leaves us with a G in front of the tan 40. And now, last step to get G by itself is we're going to take both sides and divide by tan 40. So G equals 8.5 over tan 40. Now, I forget if your book does this or not right off the top of my head. I like writing it this way. Again, kind of alluded to this in the previous example. I like writing it this way because as soon as I write out what tan 40 is, like as soon as I press that button tan 40 on my calculator, I get a number that I inevitably have to round. Right? I'm not going to write down all the digits, and even if I did, the calculator's storing way more digits than what it shows. So it's either way, you're rounding in some fashion. So I like writing it out this way and plugging it all into the calculator in one step. And when we do that, 8.5 over tan 40, we get G equals, I get 10.13 if I round. That's if I round it to a couple places after the decimal. So 10.13 is the length of that adjacent side to the 40 degrees here, the length of side G, 10.13.